Hello everyone, I hope you all are doing great. We heartily welcome you all to our YouTube channel CAD CA Master. If you enjoy what you see, hit the subscribe button and turn on the notifications so you never miss an upload. Hello everybody, I hope you all are doing great. So in the previous session, we had seen how we could run the modal analysis, that is frequency analysis, to find out the excitations. Yeah, so again, whether we can even find out whether the assembly is connected properly or if we have some loose connections. So how we need to find it out. So it's all about the modal analysis. Yeah. So now in this today's session, I'll be taking you through the NVH analysis on the same pump which I had used in the previous session. So it's just a continuation of the same. So what I will be doing here is, so just imagine it's a kind of project. Okay, so you could see there is a plate which is connecting to the supporting mount and the motor and the pump, right? So uh, what I'll be taking here is the initial the plate thickness is exactly 30 mm and I could see the weight is 32 kgs. And now on this model, what I'll be doing is I'll be running NVH analysis. Let's say I'll extract the frequency response on the required locations, the critical regions. Let's say all the mount locations, all the fasteners where we have attached right there, and the globally how this motor and the pump is going to vibrate. So I'll take the COG of it, and there I'll put some the points, and there I'll extract the uh, excitations in the form of PCH curve. Okay, and then instead of 30 mm thickness, so which weighs around 32 kgs, so I'll try to gradually reduce it to a certain value. Let's say initially I'll be considering it as 5 mm thickness, so which I think approximately weighs around 5 kg. So from 32 kg, so I'll be reducing exactly to 75% of the weight, so to 5 kg. So with that, I'll be cross verifying how exactly the curves are going to behave for 5 mm thickness plate. Okay, and now I'll gradually increase the thickness. So let's say instead of 5, I'll keep it to 20 mm and try to extract the curve and then see with respect to the reference how it is going to help me out. Yeah, so if we have the target, we could consider, but right now for this analysis, it's just like I just taken this model from the internet and then downloaded it. I don't have any data which I can refer as a target stiffness curve. Let's say for each and every components or yeah the parts. So we'll be having the stiffness targets to be met. Okay, which should be less than that. So in this case, I don't have it. So yeah, no issues. So in short, what I'll be doing is I'll gradually reduce the thickness of the plate from 30 mm to a certain value so that I could achieve the model performance which is under the requirement, and also I could able to reduce the mass up to a certain value. So this is the requirement. Yeah. So I'll just quickly take you through the agenda. So same thing, I'll be doing the analysis on this model. I'll be setting up the deck from model analysis to NVH track. Be using the frequency cards, DLOADs and the Rloads, and how we need to extract the PCH curves, how we need to refer the out files, post processing, finally validation we will do it, and then finally we'll conclude our simulation results. Yeah. Well, so this is what I'm going to do in this particular session. For information, this particular pleat is here. So you could see just below the pump, I have the screen pleat, which is initially 30 mm thick. Same here. This is just below the motor. I have the pleat, which is also 30 mm thick. These two weighs around 32 kgs at the moment. And this is just a model from the internet. It is not the uh, real industrial model for information. So this analysis just for the educational purpose, guys. Yeah. Let me take you through first Rload, what exactly these are. Okay, so here you could see the definition. So this particular Rloads will be dependent on the frequency. Okay, you can see defines a frequency dependent load. This is the equation we have it to have the frequency response problems. So what exactly Rload1 does is, so Rload1 can be used when the frequency dependent dynamic load input is in the form of real or imaginary number format. Okay, if we have the direct real number, so you can just define it here. Okay, now what exactly Rload2 does? So this Rload2, it's the same again. Here it can be used with the input of magnitude or phase. In short, okay, we can use the amplitude also, delay, phase delay, we can use it. Yeah, so yeah, you could see we have the delay, we have the phase, we can even use the table decode also, we can define it for this. Yeah, remember this, very important. So here you could see the details. So if you are like, if you have more time, so you can go and refer this, what exactly this Rload2 cards and Rload1 card, okay, how we need to use it, in what scenarios these are helpful. Okay, so you could see a delay, what exactly it means is it defines the time delay. If you have the analysis in the form of the time delays, you can refer this and you can feed the information here. This is phase, so phase in the form of decrease, you can define it. Next one is the TP. What it is exactly do is it will define to the table D cards, table D1, 2, 3, like this. We will be having the tables, so it will be referred to that. So in our analysis, we'll be considering the Rload2, and we're gonna define a table D1, and then we're gonna link this to Rload2. So yeah, okay. For this, we're gonna link the D area. Okay. I hope it is clear for you guys. So please, like, if you are completely new to this, refer these all the cards and just have a basic idea about these all things. Yeah. Next thing is the D area. What exactly it is? Very important. Okay. You could see the definition. It's a scale factor for dynamic loads. Okay, we just define a load in the form of the any of the units. Okay, unit load we define. D area is used in conjunction with Rload1, Rload2, TLOAD1 and TLOAD2, as I told you, right? So what exactly I'm going to do in this analysis is I'll consider the DLOAD in the form of D area. Okay, I'll be defining the amplitude here. Okay, and then you could see we have the amplitude scale along which direction you would like to define it, f of x, f of y, f of z. So loads, you can select it and define it here. The component number, displacement in the form of coordinate system. P1, P2 is the grid point, where which point you want to extract the DLOAD. So I'm going to define that also. Yeah. So in short, I'll be considering the DLOAD in the form of D area. I'll be linking it to Rload2. Rload2 will be linked to the table D card, where I'll be considering the amplitude in the range of the frequency. Okay. Next important thing is the EIGRL card and EIGRA card. So now I'll just simply take you through EIGRA card. So what exactly it does is, so this particular EIGRL card and EIGRL card will help us to extract the frequencies, number of modes. Let's say here in the EIGRA card we have the V1 and V2 as ID also it is there. So it will try to extract the results in the range of particularly, let's say, from 0 to 1000 hertz. Okay, even you can define the increments. Let's say here the number of root desired. Next yeah, so here you could see you can define V1 and V2, very important. So up to what value could have the frequency. So in this particular analysis, I'll be taking up to 1000 hertz. So I'll be defining V2 and I'll be considering EIGRA card. EIGRL card also we can use it, but EIGRL card will be used for the simple model. So, but EIGRA card will help us to extract the results for complex models, and you can use it for the like long range of frequencies. So for that, we would refer this particular EIGRA card. Yeah, so you could see there are a lot of information about it. So you can just try to go through it and try to explore this EIGRA and EIGRL cards. Well, so next important thing is the frequency card. So now here, what exactly I'll be doing. So first you need to know what exactly frequency card is, right? So let me just show you DEF frequency. First, I'll take you through frequency card. So what exactly it will do is it defines the sets of frequencies to be used in the solution if the frequency response problem. So you're gonna define, you can extract the results directly. Let's say I would like to extract result for 200 Hz on the particular model. So what you can do is you can define 200, and I would also like to have the excitation on 300, 350, 400. You can define the values here. Okay, you could see here 12.56 Hz, 13.99 Hz. So like that, F1, F2, F3, like you can define frequency values. Okay, and then you can extract the results. This is for FREQ. Okay, frequency card will help you to do that. But what about the FREQ1 card? So here what I can do is, you can see, defines a set of frequencies to be used in a solution of frequency response problem by a specific of starting frequency, frequency increment, and the number of increments desired. Okay, so FREQ1 card will help me to define the range of frequencies, how much you would like to extract. Okay, up to what value I want to have the result. So in short, in this particular analysis, what I'll be doing is I'll take the FREQ1 card and I'll define the initial value f1 as 0 Hz, and then increment. You can define 1 also, you can define 5 Hz, 10, 15, like that, increment, and total number of increments, NDF, number of frequency increments. Yeah. For example, you could see here, if I consider f1 as initial first frequency 0, okay, increment I'll set it to 1, and if I define 1000 here, what it does is from 0 to 1000 Hertz it will try to have the frequency response. Got it? And then excitation will be having it, and then if you want to link it for the NVH analysis by using the curves and acceleration, velocity, you can link it to that. Clear? So this is how we can use the frequency cards. There are FREQ2, FREQ3, FREQ4, 5, and all. So if you want, you can explore more about it. I hope it is clear. So I just wanted to give the brief summary or the basics of the cards which I'll be using it. So I hope it is clear for you guys. And yeah, let's jump into the model and try to set up the model and run it and finally validate it. Okay, so now we'll define frequency card. So we have the EIGRL card, right? So here we'll take the frequency. Here you can take the FREQ1 card. Okay, you can just go to OptiStruct help, and then you'll get to know what exactly it is. So right now I'll be defining the increment 1. So it should start from the 0 Hertz, and it should have 1000 up to 1000 Hertz. It should have it. Okay, so that is what my requirement is. So now once you define that frequency range, you need to define the table D card. So for that you can just search for table, and then you can switch to NIV option at this corner and just select the table D1 card. Okay, so here I'll be defining the amplitude versus frequency. So I'll just give the TID number for my reference, and I'll define up to 1000 Hertz. My amplitude should remain same, 0 to 1000. So here you can even vary depending upon the need. Okay, so for me I would like to keep it constant. Yeah, well, you can just rename it here. So I'll be taking it as frequency versus amplitude, just for our convenience, so that we can understand how this table D card is defined here. Yeah. So once you're done with that, I need to define the DLOAD. So for that, you should go to DAREA. So here I have it in the general. So you can just select the point where you would like to define the DLOAD. So I'll be selecting this shell RPE2 center point as the reference for the excitation. So I would like to define 1 as an amplitude. Okay. Similarly, I'll do for all x, y, z directions. So now I have defined it for x. Now I'll just define it for f of y and f of z. Okay. So you can keep amplitude 1 or 1000. It depends. Means it all remain the same. So anyway, amplitude I would recommend you to keep it 1 in most of the cases, so that yeah, you can just take the outputs for the Q graphs. Now I'll be defining this particular DLOAD for each and every point, the mounts. Okay. Yeah, so I've taken these all the DLOADs in the form of DAREA for all the 8 mount locations and COG of pump and the motor. Okay. So now you could see SID is same, so I need to change it because I need to excite each and every particular point, and I need to get the curve on each and every grid point which I have defined it. So I'll be changing the SID for each and every DLOAD card which I have defined it in the form of DAREA. Yeah. So now for these, I need to define the Rload. So where I'll be considering the Rload 2 as a reference here. So here I need to link the DLOAD. So in the form of DAREA I have selected. So first Rload 2 is linked here, and then via Rload 2 is I could able to define the table D card. So you can just see here. You can just choose the table D which you have defined in the TB. Yeah. So I have kept the fees delay as default. I haven't changed anything. Yeah. So likewise, you can define all the Rloads for each and every DLOAD which you have defined it, so that you can link this particular table D cards. Yeah, I'm doing it for the same. Yeah, once you're done with this, you could see I haven't defined the table D for these all things, so you can use the shortcut. So you can select all and modify and just define table D for each and every Rload. Yeah, so this is done. You could see I have defined it the excitation, the amplitude along XYZ. Yeah, so this will excite in the all the 3 degrees of freedom translations XYZ. So I would actually need only along Y, so I can just delete all the things because this is like our main focus is only to check Y. If you want, you can run for everything. Yeah, no issues. Later we'll see. Now I need to define EIGRL card. So here I will take the EIGRA card. So because I'm going to run the longer run, so my requirement is up to 1000. Yeah. So I'll be deleting this EIGRL card. So you can't directly delete it because it is linked in this header which I have defined it. I'll just simply change it to some other value. Okay. And now you can go and delete the methods EIGRL card. Okay, EIGRL to run the simple modal analysis, but EIGRA card will help you to run bigger and the complex models also. Yeah, so I'll just again change the header. The structures defined at 3 there, so we have changed it to default 1 EIGRA. You can go and change it to 1. Yeah, so you can now it's time to define the deck. So I'll be removing this whatever the deck which I have created earlier to run the model analysis. Yeah. So here I'm doing it manually, guys. So in Hyperview you can just do it by using the tools which they have given. So here I'm just doing it manually. Structures, it is 3 as I told. I'll change it to 1. So this is done. Now for this I need to call the FREQ cards. So what exactly it does is, so EIGRA card up to 1000, so increment up to 1000 we have taken FREQ1 card. So from 0 to 1000 hertz, so it will extract all the excitations, in short all the modes. Okay, and then we can plot the curve for all the required grids which we have defined there. Yeah, so we have defined it here. Next, this is fine for us. So what methods and frequency these things will do, as I told, so it will try to extract up to 1000 hertz modes and excitations, so which will help us to plot the yeah, graphs. So we'll get the PCH curve. So now I'll start defining the subcases for each and every mounts which I have considered. So I would like to define the label also so that we can remember. So we have a motor as well as the pump mounts, right? So you can name it accordingly. So pump mount 1, so 2, 3, 4. Similarly, for the motor mount 1, 2, 3, 4, you can do it. Yeah. So for example, this is subcase 1, so I have labeled it as pump 1. Yeah, pump mount 1. So label is done. So you need to call DLOAD here. So whatever the D area I have defined, you can call it here. So yeah, DLOAD, just shift question mark here. So it will take you to the location. So you can just select this. Yeah. So if you are going to deal with the like inertia relief method, you don't need to define the SPC. So later we'll think of what to do. Yeah. So now I would like to extract the PCH curve here. So displacement. Yeah, so you can extract it for the velocity as well as displacement. Right now I'm not looking for the velocity. If you want, you can even extract it for further investigations, but right now for me I need only the PCH curve. So tabular testing presentation in sort 2 I'll take it, and output medium is a punch format, and yeah, output format complex output as a phase. Yep, so now I need the set. So I need to extract the sets for each and every grid so that I can get the plots over there. So what I'll do is I'll just search for the set here, set new, and you just need to select these all the 8 or 9, 10 grid points as a set. Okay, you can even name it. So this is yeah, pump mount grid 1, like that. So output type as a grid, I'll take it. Type is orchestra. Yeah, so likewise you need to do for all the 10 grid points which you have considered to extract the results. So I'll quickly do it. Yep, so for all we have done it. Now in the header you can go to the subcase 1. So here you can call for set 1, the pump mount 1. Okay, so remember, while defining the set, it should be proper for you so that it should be called properly here. So you can even cross verify later, so don't worry about that also. So first you define your all the load steps. So what I'll do is I'll copy this one multiple times. I can paste it and I can just change the DLOADs and the punch file grid points. I have pasted it multiple times. I'll go up now. So first one is done, subcase 1 is done. So similarly I will do for the subcase 2. can just likewise, so as I'm doing, so just change it to subcase 2. This should be mount 2, and here DAREA I should call for the DLOAD, so it should be the second one, and here it should be grid number, set number 10. Yeah, well, likewise you do for all the subcases. So in short, each and every subcase will help me to extract the independent separate curves in short. Yeah, so once you are done, you could see this is how it looks like. Now, as I said, I would like to focus only on excitation along y-axis. So I would like to delete all the other excitations, because it will again simply consume a lot of time for me. So I'm least bothered about these X and Z excitation. So yeah, in short, for this analysis you might not be needed this one. In short, it is just your like analysis which I'm doing it here to just to show you how we can use this NVH analysis to optimize the component as per our requirement. So yeah, you could see all only along Y. So I'll be again changing the same. So we have taken it for all the mounts, so I need to delete f of x and f of z subcases that I have done it. So here I just need to call it again, so that is what I'm doing it here. Yep, so similarly you can just cross verify everything. So for subcases, have you properly selected the sets? So particular DAREA DLOAD should be having the same set point so that it can plot the curves properly. Yeah, so now I would like to check the weight of it, because I would like to add the self weight in the form of force. So the mass of this particular pump would be, here it is 128.8 kg. So what I can do is 128.8 into 9.81. If I do it, I can convert that particular mass into a force, that is Newton. So I'll take it approximately 1300 because it is 1200 and something. Yeah, I just want to check how the self weight is impacting on the supports, so supporting mount and the plates which we have defined it, right? Now you could see I have defined it along Y. This is fine. So similarly I'll do it for the motor 2. The motor point is this, so I need to again check the mass of it. Can just isolate that particular motor. You could see where we have defined it, it's fine. The PID I'm just isolating. So yeah, deck report, mass, this is the entity I'm just selecting. You can even go for the visible also, that's fine here. 245 kg, so into 9.81, so approximately 2400. In the sense I can define it as 2500 Newton. Yeah, so 2500 Newton, so that is the reference point. Now important, that particular COG point which we have considered, that should be connected to the mount and motor, right? So it is independent now. So if you even excite it, that is also independent. Even if you apply the load, that grid is free and it will simply move the model. So for that, you could see here that we have the properties. So just check the thickness. So all the shells should be kept at 0.01 because there's all of the solids now. You could see this plate has thickness of 1 mm, so I would like to make it 0.01. And the shells, which the main focus of the today's session is on that particular shell pleats, so having the thickness of 5 mm, that's fine. So let us see now. Yep, just simply cross verify. The moment of inertial relief method is there, I'll just remove it because I have the SPC model into it. So structural, I can consider that. So if you want, you can remove these some of the param cards So as I keep it for all the analysis defaults, so I'll just simply keep it. So if something is not needed, the solver will show that this is not required. It will show in the form of warning. So now I'll be adding the SPCs for each and every subcases. Correct. So that is important. So I'll just copy this one and I'll just paste it for all the subcases. Yeah. So right now I have the subcases only for the excitations. So I need to even select for the load. You could see how the load separately SID is single. So in the sense, whatever the loads I have defined it, 1300 and 1500, it is combined in a particular load set. If I go here, 31 is the same. So I can rename it. So now, in short, what exactly this load set has is both has combined 1300 plus 1500 loading conditions are there. So these two loads will be applied in a single subcase only. Okay. So now if I define subcase, so on that grid set will be taken. So it is not like 1300 loads. I need to get the results on pump, and 1500 I need to get it on motor. So both the loads should act in single subcase and I should get the results. That is what it is. Okay, in the form of set we have defined. So this is subcase 11. So here I should have it as load. So the label you can just remove it as, you can rename it so as weight. Okay, self weight impact. So SPC is needed here. Load I can just call it. You can just call weight load set. So shift question mark. Just scroll down, BC set here, this one. Yeah. So now you need to refine the speech, like remove the PCH curve. It is not needed. I need to extract the displacement stress for this particular subcase, right? So you can do the same here. You can just simply type in Hyperview. You can simply go and select the output formats for each and every subcases, and you can even define it globally here also and there also. But here, only thing is you need to manually define it. Yeah. So now, species 1. So I would like to call for displacement output. So you can just type everything here. Output all you can select. Yeah. So similarly, I would like to have these trust results. Yep. So I think most of the things are done. So now here I would like to change it, because each and every increment, if I take it, it will take a lot of time. So what I'll do is 5 increments. I'll take 0, 5, 10, 15, 20 like that. So here multiplication of 200, if I do it up to 1200, like 1000 hertz will be there, right? So I can just define it as 100 here. Sorry, 200, 5 into 10, yeah, 1000 hertz. Yeah, just to save the runtime. So I just did this particular change, guys. You can even run the same. Yeah. So now, as I said, that particular motor COG point is independent. So what I'll do is I'll just select this particular shaft as a reference for RBE2, and I'll just connect this one to that, right? So this is one RBE2. You can even select whole model and define it. That is also fine. If we do it, you might get stress hotspots, because the load will tend to consider only these grids and it will impact on it. Anyway, it will be distributed for this whole model, as analysis is just approximation, so I'm just doing it roughly as it is self weight. Yeah, practically if you think so, I should consider whole model, and then I need to consider the load impact, correct? So here I'll just select this face as a reference, middle click. Yeah, so now what I need to do is these RB2 reference points I should paste it to the COG points of the motor and pump. So you could see here I have defined it, right? So you can just select this one and paste it here. The COG while we considered during the excitation implementation, it is slightly moved there, so no issues. It's again an approximation. So this particular load point, I'll just simply paste it here. Yeah, this is done. So we can output this now. So in short, what we have done is we just connected RBE2s for this COG point so that it should be linked to the pump and motor. Now I'll just import the model in Hypermesh. So go to import solver tag. Just select the NVH on pump. Okay, open it. While opening, you might get some warnings and errors. So if it is not, then your model is fine. Good to go with this. See, everything is fine. So now just go to analysis bottom, just select the OptiStruct and type as analysis. Click on OptiStruct, just replace it once, and then solver will start to run by using the compute console solver. Yeah, I can just keep it here, so it will take some time. So as I try to make it as simple as possible because I don't want to run it for a long time. So you could see we have the results. OptiStruct job completed. You can go and you can just see the output also. Yeah, so now all the 10 subcases will have the PCH curves. Only one subcase 11, will have the stress and displacement requirements here. We'll just cross verify the same. You could see this is the displacement, least displacement we have it, because as I said, it's just a self feed. It is not impacting much. Your model is also fine because there is inappropriate movements. So stress wise, you could see it is 174 megapascal, so it should be the stress hotspots. As I said, you could see if you zoom in, so this is the region, so we have the stress hotspot, right? Because the whole the load, the Newton which we have defined in the form of mass, it is impacting on that RB2 locations only. So if you have considered whole model, if you have selected RBU2 for the whole model, then you might not be having this one. So yeah, very important. So while you define the boundary conditions, you should take it properly. So yeah, so here also we considered, right? So I considered RB2 for the shaft and the support also for information, guys. Yep, so this is fine, no issue. So I'll switch to hypergraph now because we need to plot the graphs, right? So how all the mounting locations are getting impacted. So for that, I would like to go to file location. So I need to extract this PCH curve. So you could see these are all the subcases 1 to 10. So I would like to extract the displacement. This is the point which I'm calling for the displacement, and I would like to have a long Y translation. Correct. Before doing it, I would like to consider the stiffness as a reference. For that, I'll go and I'll change the math expression instead of displacement to stiffness. So how are we going to change it? Inverse of displacement is stiffness, right? So you can just do 1 by V. So in short, it will be considered as stiffness. Correct. And even take it as displacement. If it is more displacing, then anyway the stiffness will be less stiff. But right now I'm considering directly the stiffness. You could see a particular, let's say a near to 300, approximately 300 plus 320 or 310 hertz has a big sudden jump. Correct. So we'll see for the for other mounts also, all the 10 mounts will plot it. I'll just quickly do it. So you could see this is the second mounting location. It is not impacting much. This is fine. This mount, yeah, this also has the huge impact. It's overlaying on the first mount, slightly less. Correct. Yeah, pump mounts 1 2 3 4 is done. Now motor mounts will plot it. So these are the excitations. Now if you're dealing with automotive industries, definitely you'll be having the target, so you should not cross that target, stiffness target, but this is, I'm just doing it as a reference. I don't have any targets here, so if the especially pump industries are looking to optimize this thing, so they would know, or they would need to set the targets so that it should not excite above this particular stiffness target likewise. Yeah, ideally it should be 10 raised to 5, okay, 50,000 or yeah likewise, but it is too much in the sense we have considered the thickness plate of 5. So as I told you, right, so that is default, it was 30, so we made it to 5. So I'll just hide these all the curves. And you could see I would like to only see the mount, I mean the COG of the motor and pump, so how it is exciting. So I could see they are well within the limits, right? So if I hide this one, getting confused, so there's no hide option, so I just need to click on this icon. It's done. So the point, you can refer this points, okay, point ID is written, right? So you could see it is 7956725. So you can just hide it directly by seeing it. Now last two, you could see 7848 and 7998. These two has the peak. When this is the point, you could see how much it is, 265. This is peak. I think this is fine. But when it comes to the first mount point, if I just try to plot it here, it is 310, the huge deviations. Now what I will do is, now we got the curves, right? So we got to know how it is exciting and what are the critical regions for us. So I'll just see which are these mounts. So this is the mount, okay, which is having more excitation. Likewise, I can check for whatever the PSH curve I'm having there. I can quickly cross verify which and all the mounts are getting impacted much. So you could see these all are the grid points. These are the points. So what I can do now is I'll change the plate thickness. So initially it was 30, so I don't know the mass of it. Later we can conclude it. So what is the mass? So now instead of 5 mm thickness of this plate, we will slightly increase it to instead of 10 or 15, or we can even keep it 20 mm also, right? So initially it was 30. Now let's see what we can do is I would rather change it to 20 would be good, or yeah, 20 is fine for me. Now if you want to see the difference, so initially it was 5 mm thick. Now what I did is I increased the thickness to 20 mm. So you can just go to presentation parameters, so it should be here. If you right click in 24.3, you used to get it here, but right now in the settings, here you have the presentation parameters. Click on it. Here you have the draw shell as solid, so that you can visually see how thick it is. Yeah, initially it was 30. I reduced it to 5 mm so that I wanted to see if I reduce it to 5 mm whether it is going to impact on the stiffness of the model, or it is working fine or not. But I could see there is a huge peaks are there, the drops are there. So in 5 mm thickness I can't make it. So what I have done is I have changed it to 20 instead of 5 now. Now this is again, I'll just output this as a separate FEM file. Right now it was 5 mm, so now it is 20 mm plate thickness, right? Okay, so once we output this, we'll again run this model, and I'll just yeah, save this session because later on I can just load that all the graphs in this. So I'll just import this model again. I'm just using the OptiStruct solver to run, so import this model. So now it's 20 mm thick. Just you need to run it. So these are the warnings, no issues. I think it's fine. Yeah. So now just run this model. Go to OptiStruct, analysis type. So replace this, overwrite the model. Yeah. It will take some time. So in short, I hope you got it, guys. So I had a model of plate thickness of 5 mm. So we ran it and we had seen the stiffness curves for each and every mount regions which we are looking for. And now I have changed the thickness to 20 mm. So I ran it now. So I'm just opening this same session file so that I can load this particular PSH curve here also. You can just go to File, Open. Yeah, 20 mm PCH. You could see NVH on 20 mm plate PCH. Just open this. You could see all 10 subcases. So just plot all the plots. So yeah, before that you need to change the equation, math expression to stiffness from displacement. Yeah, so you could see this is the plots we have it. It is in dot format. Later you can change it. And now let me do one thing. I'll just load all the plots quickly. Yeah, now we'll try to compare one by one. So this is the mount 1. So I'll just rename it for my reference. So grid point is 795617717. So I'll just rename it as mount 1. So the color also could change it to red. Okay, just for our convenience, how the stiffness is getting impacted. Now we can just see. So this is the mount 1. So similarly, you can come on this point, same 79717, the same grid point. So this is optimized one, right, in this sense. So I have increased this plate thickness to 20 mm. So same, it is mount 1 also, mount 1 the same. So you can just name it as optimized. So initial one is the reference one, this is optimized one. Yeah, and I can show this. So here also I'll take it as red. So yeah, it should be the same curve, right? Can have the dotted format, it is there. So I don't need to change it, it's the same. So I'll just, yeah, have it here. I'll just simply show this plot now. You could see the peak got reduced drastically. Great, right? So similarly, I'll use this one. So mount number 3. So I'll just rename it as to mount 2 because this is the peak one which I was facing the issue. So yeah, this is fine, green. So I'll again take the same one here. I'll just rename it. You could see the peak. It got reduced to 10 power 7 to approximately like half of it, right? The drop is improved drastically. Great. So yeah, just keep it a screen. You could see likewise. This is how the we can see the impact of the pleats, right? The how we can just play around and how we can optimize the model. I hope you people are clear with this. So this is how we can just run the NVH analysis and try to get the flaws and check for the excitations if it is beyond the target limit. we can try to improve a model, and then yeah. So just to show you guys, so I just took the reference model of 30 mm plate thickness. So purposely I reduced it to 5. Show you how we can run the NVH and see how the excitation is happening. And if I even keep that to 30, that's well and good, no issues. Now I'll show you how much mass we have reduced and what is the mass savings of this. So anyway, it is 20, and I'll just isolate these two. And for 20 mm thickness, what would be the mass of this particular pleats? Let's say if you're going to manufacture it, what should be the mass? Correct. So here if I see it, it's 20 kg approximately. Correct. 20 kg is too much, right? So if you could save at least 10 kg for automotive components, if I even save 1 kg, it is more than sufficient for the whole model. So here, per particular motor assembly, if I could able to save 10 kg is fabulous, right? So now if it is 20 thickness, it is 20 kg. Now if I even consider 30 mm thickness, then it is 30 kg, right? Approximately. Yeah. Now we'll see how it is going to impact now. I would like to see the 30 kg model, the reference model, how much it was. Let's see. I could see, oh, it is 31.2 kg. So in short, we have optimized the model to 10 kg. We have reduced the mass of 10 kg. Great, right? So yeah, it is just a reference for you guys. So what I thought is, if I keep the 5 mm plate thickness, then it is only, I think, 5 kg, right? So we would have saved 26 kgs, but that is not that didn't help us, right? So we had seen that the stiffness curves at 265 and 310 Hertz were shooting a lot. That might tend to a failure at a particular working scenario. So better to keep it low. So what I did is, instead of keeping 5 mm thickness, I went ahead to keep it to 20 mm thickness, so that I could save on an average 10 kg mass saving. So if with that I ran the model, and then I could able to see the drastic improvement in the stiffness curves. So it got reduced drastically. And then if we would have had the target curves, and then we would have properly validated the model, and we would have seen it. But yeah, I hope this particular analysis might have already helped you to set up your models for different analysis, run the NVH analysis, vibration analysis for a particular range of frequency, and extract the curves at a points where exactly you're looking for the critical regions. And if you might have already known the targets, if it is hitting the target or if it is more than the target, how we can improvise it, let's say by changing the thickness or optimizing it or doing other things. Yeah, so then again running the validation and checking with the targets. If it is less than that, then well and good. And then yeah, so this is how we can deal with the NVH analysis for simple model. And I hope you people can do it for all the models which you can for your industrial references. Yeah. Okay. Well, finally, to conclude, I'd like to take you through a few assumptions, and I would like to conclude with the validation here. So initially, the model, the plates which you could see here, these two were weighing around 32 kgs, and the thickness was around 30 mm thick, correct? And then what I did is, for this analysis, I consider the least possible is 5 mm thickness here for these plates. And for that, I try to run the NVH analysis, and I could have the reference model as the 5 mm thick plate pump model. Okay, for that I could see the plot around at 310 Hertz. My stiffness curve is peaking up and shooting up above the target. So target I have imaginarily considered as 2 to e raised to 7 as my stiffness target. Yeah, so it is shooting up. So in short, whatever the 5 mm thickness I have considered is not going to help me out to reduce the weight up to 20 kgs. So that is not possible with this plate. Yeah. So next, I could see the same for the mount 2 also at around 310 Hertz. The peak got reduced. Peak is drastically decreased. You could see at 310 Hertz, I have a least one 5 e raised to 6, and this peak got slightly shifted around to 300 Hertz, and which is below the imaginary target which I had considered 2 e raised to 7. And this is with the thickness of 20 mm, and the mass of the plates are here as 20 kg. In short, from these two PCH curves, I could conclude that if I could able to make this particular 30 mm thick plate to 20 mm thick model, which will tend to save me 12 kgs of mass, a potential mass. This is just a approximation I'm doing it, as I'm just running this as a educational video where I could able to show you the potential mass savings if we try to run the NVH analysis to save the mass. Okay, and now with this I could able to save around 12 kgs mass, right? So, and the peaks mount points, these 4 points and these 4 points, I could see on these peak points I could able to reduce it, right? And then it is meeting the target also. In short, so with this kind of analysis, we can reduce the mass of any of the industrial component by running the NVH analysis, setting up the target using the industrial given target and running the validations and reducing the mass will help us to save the manufacturing costs. Yeah. Well, so this is what about the conclusion which I would like to put. So yeah, finally to summarize, we had gone through the deck preparation in ANSA. If you want, you can prepare it in Hypermesh also. Yeah, we had seen the basics of DLOAD, Rload, frequency cards, how we can use them and set the deck, PCH curve extraction, and getting the output files, post-processing them and validating, and finally we have concluded. And yeah, so we could able to save a certain mass, right? Well, that's all about the summary here. And then right now I just want to just put one particular request. If you would like to have the trainings from our site, you can directly contact us to a given number, or else you can write to our mail so that we can get back to you, and we can even give you the personalized trainings, or else one-on-one sessions, whatever it is. Well, so contact us if you're looking for the trainings from our site. That is what I would like to ask you guys. Well, that's all about the session, and we will bring again new contents for you guys. Thank you all. See you.
We heartily thank you all for watching this video. If you enjoyed this video, don't forget to hit the subscribe button and give it a thumbs up. Follow us on Facebook, LinkedIn and Instagram for behind the scenes content and the updates. Stay curious, stay awesome, and see you again in the next video.